So let's go ahead and take a look here at some Lewis dot notations, and really what we need to do for Lewis dots is get our 5 steps here down. Go ahead and pause the video right now, take a second to get these notes down, and let's start with our first example. For carbon, 3 hydrogens and 1 iodine, we are going to write and draw the Lewis dot structure for this molecule. So first and foremost, we need to determine the type and number of atoms in each molecule. We have 1 atom here, 3 here, 1 here. The electron dot notation for each. Carbon is in group 4A. It's going to have 4 valence electrons, so we have 4 electrons represented there. Each hydrogen is going to have 1 lone electron, and the iodine here is going to have a total of 7 electrons in its outermost energy level because it's group 7A. The total number of valence electrons for each here is going to be 4 plus 3 plus 1. So adding those up, I have 4, 5, 6, 7, 8. Oh, I'm sorry. This is 7 here. So that's 10, and 14 total electrons is my total there. So I have 14 electrons basically to fulfill my octet rule here, which is to get 8. So I want to arrange them so that the electrons line up. And really, what does that mean? Well, I'm going to take my carbon here, and we're going to learn here shortly why I want to make carbon my central atom, but it's going to be my central atom because I have 1 on each side, and I know that I need to match carbon up with iodine. I see iodine has this little lone electron right there. Well, that little lone electron actually wants to bond up with carbon, forming a bond right there. So my iodine I can represent, that's the 1 electron, 2, 3, 4, 5, 6, and 7. That's my 7 electrons for iodine. Where I have hydrogen, I have 3 of them. And hydrogen each has 1 to give, and this is going to fit perfectly because if I stick 1 hydrogen with its 1 electron there, 1 hydrogen with its electron here, and 1 hydrogen with its electron there, I get an octet. And what does that mean? An octet. Well, look at carbon. It has 8 electrons surrounding it. 1, 2, 3, 4, 5, 6, 7, 8. They're not all carbons. 1 of those is iodine. 3 of those are hydrogens, but it's sharing to get 8. Iodine has 1, 2, 3, 4, 5, 6, 7, 8 around it. And remember, hydrogen's the exception. It only needs 2, so it's sharing 2 electrons. Now, basically, what we can do from here is take our dots, and basically each bonding pair we can represent as a line. So hydrogen is going to bond with carbon, is going to bond with iodide, bond with hydrogen, and bond with another hydrogen, and then you just fill in any lone pairs that are left over. That's our first example for Lewis dot structures. Our next example here, let's take a look at our next example, which is C2H4. So now I'm dealing with a little larger molecule that has a few more electrons in it. And again, my first step, I need to determine how many carbons or how many electrons carbon has. Each carbon is going to have 4 valence electrons. So that's 2 times 4 plus hydrogen. I have 4 hydrogen atoms, each with 1 valence electron. So I have a total here of 4 plus 8 is going to give me 12 electrons I have to deal with. And again, I'm going to set up here my structure. Now carbon, again, 1, 2, 3, 4. Another carbon with 1, 2, 3, 4. And then I want to put in my 4 hydrogens. Well, really the hydrogens, you know that the hydrogens are looking for those lone pairs. So I'm trying to put a hydrogen here and a hydrogen here. I'm just going to do it evenly, put a hydrogen there, and I want another hydrogen here. So right now I'm at 12 electrons. Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can use no more electrons. I can't use any more because they're all used up. I know that these two are going to form a bond. these two electrons are going to form a bond, form a bond, and form a bond. So those are going to be lines, and these are bonding. As far as carbon goes for its octet, 2, 4, 6, 7. It has 7. Carbon here, 2, 4, 6, 7. It needs 8. So what can happen is basically these can slide down and they can form a bond between them, and we end up with what is called a double bond. So this ends up looking like a hydrogen bonded to a carbon with another hydrogen down here, a double bond between the two carbons, and again my hydrogens are going to basically be on the corners. This one would be up here a little bit because repulsion between them puts them at their furthest angles from each other. And to check my octet rule for carbon, check your octet rule. You're going to have 2, 4, 6, 8. So that would be 2, 4, 6, 8. And same for this carbon, 2, 4, 6, 8 around that carbon, each hydrogen with 2. And I've only used 12 electrons. 2, 4, 6, 8, 10, 12. So all of your work checks off okay, and that is a good example of Lewis structures. What I'd like to do right now is take a short time to watch this video that explains this HONC rule. And it's a rule that we can use to help with writing Lewis dot structures and drawing them, and it really makes sense.
When drawing Lewis structures, we rely in large part on the octet rule, but I also find it useful to teach students the HONC rule. Now understand these are rules, they're not immutable laws of science, and so there are going to be exceptions. Nonetheless, most of the time these rules apply, and they help us in deciding how many bonds will be around any given atom in a covalently bonded compound. So it goes like this. Hydrogen and the halogens will form one covalent bond in covalent molecules. Oxygen and the oxygen family, meaning the nonmetals in the oxygen family, will tend to form 2 bonds. Nitrogen and the members of the nitrogen family, in particular phosphorus, will tend to form 3 bonds. Carbon and the carbon family, in this case limited to silicon, the only other nonmetal, will tend to form 4 bonds. If you look at the periodic table above, we have hydrogen and we have the other nonmetals, excluding the noble gases, which tend not to form covalent bonds. So let's look at how this is useful in drawing Lewis structures. So hydrogen in a chemical compound will tend to have a single covalent bond, because hydrogen will only end up with 2 electrons around it. That bond, which is essentially 2 shared electrons, will suffice. The halogens, on the other hand, we'll take chlorine as an example. The HONC rule says chlorine will form a single covalent bond. To get its octet, it's going to have 3 pairs of electrons that are not shared covalently. And that will be true for the other halogens as well, fluorine, bromine, iodine. The members of the oxygen family tend to form 2 bonds. Now there's 2 ways that that can happen. Oxygen could have 2 single bonds, and that would necessitate 2 pairs of unshared electrons, 2 unshared electron pairs. Another possibility is that oxygen could form a double bond with one other atom, and again we're going to get 2 unshared pairs of electrons. Nitrogen in the nitrogen family, tending to form 3 bonds, can do that 3 different ways. Nitrogen could form 3 single bonds, which would require 1 unshared pair. Nitrogen can form double bond and a single bond for 3 bonds total and an unshared pair. Or nitrogen can form, as it does in hydrogen cyanide, a triple bond and 1 unshared pair. Notice there's some generalities here. The halogens are always going to have 3 unshared pairs around them. Oxygen, 2 unshared pairs. Nitrogen, 1 unshared pair, which should lead to the conclusion that carbon will not have any unshared pairs in most covalent compounds. So carbon's possibilities are going to look like this. Carbon can form 4 bonds. It could be 4 single bonds. That gives it an octet, no need for unshared electron pairs. Carbon could form a double bond and 2 single bonds for its 4 bonds. Carbon could form 2 double bonds, or carbon can form a triple bond and a single bond. There's no such thing as a quadruple bond. And in all of those instances, carbon gets its entire octet from the bonding electrons and has no need for unshared electron pairs. That's the usefulness, again, of the HONC rule.